One of the concepts that we're starting to build towards is being able to tell if something we did, say an experimental manipulation, actually did something. Now, to do that, you have to take one sample, give it the manipulation, take another sample, and don't do anything to it, and then compare the mean values. And then you look at the difference between those two sample means, and then you make a decision. Are these means different enough that we think the experimental manipulation changed the mean of the one group? This raises the question, how different is different enough? Now, to actually understand that, one of the things we need to do is look at sampling error and how much sampling error we should expect. Because we could, just by a random chance, get two samples, and odds are the means will not be the same, even if they're coming from the same exact population. So to answer the question of how different is different enough, we have to delve into some of the nitty-gritty of random sampling, and we have to look at something called a distribution of sample means. Now, that is kind of abstract because it's really an entirely new distribution made up of every single possible sample mean you could draw from a population. So that's what this video is going to be about, the distribution of sample means. Now, before we get there, we need to spend a little bit of time talking about random sampling. Now, you'll notice the header for this slide is random sampling in inferential statistics. Inferential statistics is that determination we would eventually make. Are these two samples the same or are they different? Are they coming from the same population or not? And they're based on the probability that two samples come from the same population, specifically two random samples. Now, when we say a random sample in this context, what we are very specifically meaning is a sample produced by independent random sampling. Now, this is of the utmost importance because only when we have an independent random sample can we get the probability of that sample occurring by chance. Now, to do this, you had to have sampled the sample with replacement as opposed to without replacement. Meaning that after you pull one person out of the population, you have to put them back into the selection pool before you get the next person. So that you actually can potentially sample the same exact person 2 times in a row. Now, part of the reason we're spending so much time on this is because if you have a population and you pull an independent random sample from it, as you can see here in the 2 histograms at the right, the population being the one that's a little higher up, normally, and we hope that the population mean and the sample mean are somewhat close to each other, 3.5 to 3.33. However, notice that they're still not equal, and that's because any sample, regardless of how representative it is of the population, is still a sample. It's not the entire population. There will be a difference, there will be a discrepancy between the population and the sample. This difference is called sampling error. So if we were to formally define sampling error, it's the natural discrepancy or amount of error between a sample statistic and its corresponding population parameter. Now, the term error is specifically used because we are trying to estimate the population mean based on the sample mean. Consequently, any difference between the population mean and the sample mean is actually how much error there is in our estimate, how far off we are, how big of an error did we make. Now, it's important to recognize that you can get different samples from the same population, and they're not all equivalent. Some are better than others. For example, here on this slide, we now have two different samples. One sample mean has a mean of 4.67, the other 3.33. One of these is much closer to the population mean than the other. Now, the question we really want to ask is how likely are we to get a sample mean that's that extreme, that has a mean of 4.67 or greater? So what is the relationship between the population mean, the sample mean, and the probability of getting that sample mean is really what we're kind of driving at here. Now, in order to do that, what you have to do is create what's called the distribution of sample means, where you take every single possible sample that you could get from a population with a specific sample size, and then you create a whole new data set, a whole new distribution made up solely of the means of those samples. So in this instance, what we have now is the raw scores for this new data set being the sample means of a population, all the possible sample means specifically. All right, so let's take this population, okay? Population X. It has a mean of 5 and a standard deviation of 2.24. There are 4 scores in this population, 2, 4, 6, and 8. So it's a very small population, but it's going to help illustrate this. What we're going to do is we're actually going to take the time and create this distribution of sample means. Is I am retranscribing the population, and then what we're actually going to do is we're going to set up pulling out all these different samples. So we'd have a given sample, the first score in that sample, and the second score of that sample. So all the samples with an n of 2. Pull out 2 to start. Now we have to place it back in the population, so the next score we would actually could potentially get is 2 again. 2 and then 4 for the next sample. For the next sample, we could get 2 again and then pull 6 out. Then we could get 2 and 8. That's all the possible samples where 2 is the first number we select. Now let's get all the ones where 4. So we get 4 and 2, 4 and 6, or excuse me, 4 and 4, 4 and 6, 4 and 8, 6 and 2, 6 and 4, 6 and 6, 6 and 8, 8 and 2, 8 and 4, 8 and 6, 8 and 8. Now, we just need to calculate all the means of these given samples. In addition to figuring out how many possible samples there are, 16. Now let's go ahead and get those means. So 2 plus 2 is 4, divided by 2 is 4, and so on. So right here, I'm just calculating out all the different sample means. And it's just sort of this slow, tedious process, which is why the video is sped up to 2 times speed, 3 times speed, pending. All right, now that we have all those means, let's go ahead and give ourselves a little histogram here real quick that we just sort of sketch out. So I'm just going to go through and input all these means into this little histogram. It's not the cleanest histogram in the world, but it illustrates the point that we're trying to make. So we're sitting here and we're watching where all these sample means tend to pile up. So first thing you should notice that these sample means are actually clustered around 5, the population mean, and it's also symmetrical on either side of 5. Now, these two properties hold true for every single distribution of sample means. Again, as we observed, all of those sample means tend to pile up around the population mean. Most of the time, a sample mean is a good estimate. Now, as we get further and further away from that population mean, the frequency of those sample means decreases. And we can see that really, really clearly right here. Sample means of around 2 and 8 are pretty rare, but 5 is actually the most common sample mean that we have. Now, the other thing to note is it forms a normal-ish distribution. Eventually it will, but not quite yet. Now, while the sample means pile up around the population mean, the same doesn't actually occur for the variance of this population, or rather the variance of the distribution of the sample mean. It actually decreases, and that's a little bit harder to see. Now, the reason it decreases is because we're no longer using raw scores. All the extreme scores in the original data set are essentially hidden in a matter of speaking. And so the distribution of sample means always tends to have less variance than the original population that these samples are coming from. Now, the larger the sample size that you have, the better estimates your samples will be of the population. So another way of stating this same exact thing is that you'll have less variability in your sample means when the sample size is larger. Now, there are a couple reasons for this, but the biggest one is that the larger the sample size, the less any one individual score affects the mean. Now, most importantly, that means those extreme scores, when you randomly sample out some person that's got a height of 7'7", they affect the average height less. Now, the bottom line you really need to remember is that the larger the sample, the more accurate, the more representative, and just the better estimate of the population mean that samples mean will be. Now, the other thing to note is that regardless of how the population, that original population, is shaped, the distribution of sample means is always symmetrical, it's always unimodal, and once your sample size is large enough, it's normally distributed as well. Now, the central limit theorem is a theory surrounding this distribution of sample means, and it is essentially what describes the distribution of sample means and the properties it will have. Now, this holds true regardless of any property of that original population. Distribution shape, mean, variance, etc. Now, the three things that it really nails down on are the shape of the distribution of sample means, the central tendency of the distribution of sample means, and the variability of the distribution of sample means. Now, the first of these properties we already know. The mean of the distribution of sample means is always going to be equal to the population mean. Now, we know that the variability of the distribution of sample means is less than that of the population. But specifically, the standard deviation of the distribution of sample means is equal to the standard deviation of the population divided by the square root of the sample size used to create the distribution. Now, this makes some intuitive sense. When you look at this formula, as n, which is in the denominator, increases, that denominator will get bigger and bigger and bigger and bigger and bigger, which makes the overall quotient there get smaller and smaller and smaller and smaller. We know that the larger the sample size, the less sampling error we have. Another way to think of the standard deviation of the distribution of sample means is the amount of error you should expect on average, because it's how far a given score is, or a given sample mean is, from the population mean on average. And then finally, the central limit theorem describes the shape of the distribution of sample means. It's always symmetrical, it's always unimodal, but specifically, it approximates a normal distribution. And it is normal once we hit an n of infinity. But for all purposes that we really care about, it's normal after you hit an n of about 30. Now, what would a theory be without a few special names? The mean of the distribution of sample means has a special name. It's called the expected value of m. The next special name that we need to be aware of with the central limit theorem is the standard error of m. This is really just the name for the standard deviation of the distribution of sample means. Now, you should recognize that term standard and be thinking standard deviation. And when we're thinking about the error of the sample mean, we should be thinking how far that sample mean is from the population mean. So we're really just looking at the standard deviation of sampling error here, hence the name standard error of m. Now, the key way we need to interpret this is how far, on average, a sample mean is from the population mean. Or if you want to get really technical, the expected value of m, which is equal to the population mean. But regardless, the key thing this tells us, and this is probably the most important concept when it comes to the distribution of sample means, is how much sampling error we should expect. So if we have one sample that has a mean of 3, another sample that has a mean of 4, and we know the standard error is 2, the difference between these two sample means, 1, is much less, or specifically half of the standard error, 2. So it suggests that, hey, these two samples are coming from the same population. It's very likely that they came from the same population. However, if we still had a standard error of 2, and that first sample's mean was still 3, but that second sample's mean was, say, 9, now there's a difference of 6 between those two means, which is really 3 standard errors of difference, or 3 standard deviations out. Now, hopefully that rings some bells. That is very unlikely, so it suggests something is going on here. So standard error is something that's going to be very critical for inferential statistics going forward, and we will begin revisiting this concept in more detail when we start getting into t-tests.